Hello, everyone. Good afternoon to those colleagues joining from UK, and good morning to colleagues joining from America. I'm Mason Qatlon. I'm a professor in Energy Systems and Network at Cardiff University. And today we have the third session of our hydrogen and energy seminar series, which started between Cardiff and University of Wyoming. Today we have one speaker from Cardiff University, Professor Agustin Valera-Medina, who is going to talk about ammonia. So off you go, Agustin. So if you can put your slide into full screen, that's excellent. Also, before I forget, there is question and answer features in this webinar, so feel free to type your questions, and after 45 minutes, which Agustin is going to talk us through the slide, we can actually go through those questions. So please do use question and answer features.
Thank you very much, Mason. Thank you very much, Mason. Thank you very much, everyone, for joining us today. And good morning to the US, good afternoon to UK. I'll be talking about insights into a future running on ammonia combustion. We've been working on this subject for some time, and I'll show you again the things we've done and how interesting this is regarding the supply of hydrogen and movement of the molecule. So just to give you an insight on how we're going to look into this presentation, I'll start with an introduction following challenges that we have spotted around this subject, developments that we have done and some other institutions, and then finish with some collaborations and conclusions that we got from this seminar. So just to give you an insight into what we have done, you have all these lists of things. So if you have the time and interest and will to then do some reading, go ahead, please. This is some of my background and the work that we've been doing on ammonia. But if you don't, one of the things that I keep reminding the audience is that ammonia is used for salts, and in NFL players and weightlifters, they tend to use it just to stay awake. So probably is one of the cases that if you have any close or nearby and you're falling asleep, just go for some and then have a sniff of some ammonia to then wake up. So for those of you that probably didn't know, this is something going on. And yes, quite interesting how it just boosts apparently what they presume again in these different groups, NFL especially, how it boosts the energy and the stamina to then carry on with the work. So yes, ammonia has lots of attractive and interesting features. So starting with the introduction, we go back to why we're doing all this, and we've been talking about renewable energies as a way to decarbonize and reduce greenhouse gas emissions. But we know as well that these sources tend to be intermittent in nature. So just to give you an example, probably you know that a few years ago, we had a big blackout here in UK for almost 1 million people suffer in the middle of the day. The reason was we were running around probably 48–50% wind power. There was a problem with the wind turbines and connectivity, and that amount of people in the Midlands lost power. And similar situations keep happening everywhere in the US, Australia, Asia, etc. So it just takes us to the point of we need some way of storing some of that energy. And there have been a lot of methods that have been proposed over the years, some of them commercial, some others fundamental in nature, but there's one that is critical for any kind of mixture that we'll have for the future, for right now and the near and long-term future, and that is chemicals. The reason for that is we've been using chemicals for hundreds, if not millennia of years, and we're talking about oils, we have methane, we have natural gas, and now these days the topic is hydrogen and potentially ammonia. So looking into this graph that was developed by Siemens a few years ago, we can then see how the storage time, when we're talking about these different potential technologies, goes from the seconds to the weeks, and as I mentioned, in the case of chemicals, even beyond that, in years, centuries, etc. And the same way goes into the amount of power that they can deliver. So not only a small power, 1 kilowatts, to actually gigawatts that can be delivered, and as we know, in power stations and large systems that will then provide us with the electricity and energy that we require. Now, one of the things that I always try to bring up is why ammonia, and then comparing it somehow to what is going on with hydrogen. So first thing is this analysis done by 2021 by the Hydrogen Council, where they were doing some analysis and then finding out what was the energy source based on the location. So here in this map that you see on the left side, you have the areas where we have lots of presence of natural gas across the globe. Now, it's not everywhere, but we know that we still have some points where to tap into these sources. But different to the case of renewable energy, where we have photovoltaic and wind resources in the upper part of the graph, where we can then tap into those resources that are almost limitless, and we can then recover from every location in the planet. And this is just photovoltaics and wind. We're missing as well marine, that has a lot of potential as well in many of these locations that are just potentially islands or next to sea locations. And based on that, and then thinking that the way forward is going into green hydrogen, one of the parts of the study was looking into how we're going to move that hydrogen. So the study was focused on three different ways to then move this hydrogen. One being ammonia, the other one liquefied hydrogen, and then liquid organic hydrogen carriers. And the analysis implied producing it in a location where there was lots of resources available, but not that much consumption. At the same time, moving it along very long distances and reaching destinations like the US, European Union, or Japan that require that high intensive requirement of energy. So as you can see from the numbers that we got in the three different scenarios, the case of ammonia, liquefied hydrogen, and organic hydrogen carriers is almost the same, between 3.5 to 4.4 US dollars per kilogram of hydrogen being moved from those locations and then converted into hydrogen, or then used at cost or being deployed at the port. But there's one component that makes a whole difference in these cases, and is that if we manage to reduce the cracking of ammonia, that's almost a third of the total cost of moving the hydrogen via this way, which means that that was the case, that we needed to then move the hydrogen long distance, then ammonia becomes the most economic solution from the lot. So that's the reason, because we present ammonia as a potential method to then move hydrogen, so a hydrogen vector. And the reason for that is not only because it's going to reduce the cost in long distance, but also because we can recover it via renewable sources. We can recover it using rescued stranded resources from waste streams. As I mentioned before, one of the things that is very interesting as well is that when we talk about long time or long distance storage, the cost of having ammonia compared to having cryogenic hydrogen or pressurized hydrogen is almost 26 to 30 times cheaper. In the same way, we can employ it in islands or isolated locations off the grid. We can now, as I'll show you in this presentation, use it as a fuel, and we've been using it as a fertilizer for over 150 years. Has more hydrogen than hydrogen itself, because we have in the ammonia molecule 3 atoms of hydrogen compared to 2 atoms that we got in the hydrogen molecule. And finally, we have a very well-developed infrastructure that has been built up over 150, 180 years that moves around 200 billion euros annually. And on that line of thoughts, and there have been lots of different methods and materials being analyzed to then move the hydrogen, as you can see here on this graph. And if you look at the very top right of the screen, where we have that part of ammonia, either cryogenic, or sorry, refrigerated, because it's not going cryogenic, it's just minus 30, minus 40 degrees Celsius. And that compare as well with the case of having it slightly pressurized over 10 bar at atmospheric temperature, is one of the materials or methods to then move more hydrogen that is available, and again, with the versatility of having a lower cost. So along those lines, there's been a lot of talks now on how we're going to then manage to produce all these hydrogen, convert it into ammonia, and then make it a feasible part of the economy, of this hydrogen economy that we've been talking about. So right now, we're mainly relying on the production of ammonia and hydrogen via steam methane reforming. But the next generation that is going to be start producing it in the next couple of years, now with companies like Yara, CEF, etc., looking into the production of this green hydrogen, is via renewable energy. So we can then use electrolysis, then produce the hydrogen, and then using air separation methods for the nitrogen, put it into reactors in a process called Haber-Bosch, and then finally produce the ammonia that we need for fertilizing and now fueling applications. So that's what now some scientists call generation 2 ammonia. But there comes a third generation that now people are starting to investigate, and it's called third generation, that essentially will start working with surface reactions, fuel cells, lithium-based materials, etc., where we'll have the combination of both water and air, using some energy coming from these renewable sources. Won't require the electrolysis of water or the separation of nitrogen, and because of the affinity of these materials with hydrogen and nitrogen, will produce the ammonia straight away, meaning that anyone in the world, as long as we have water, air, and electricity, will be able to then produce ammonia, and from there, in the hydrogen that we require. So it's probably going to be the next year Nobel Prize, and as this already has 2 Nobel Prizes in its belt, so the Haber-Bosch process, and it's very likely that if we manage to do that, anyone will have access to store and then utilize ammonia as a hydrogen vector. So for that reason, there are a lot of work going on in different areas. For example, in our case, we have been working on thermal systems. And one of the things that I want to point out is, again, this is going to be part of the final solution. It's not going to be the final silver bullet that is going to solve all our problems. It's going to be part of some of that. So if we have renewable energy or we have methane reforming, then we'll have the renewable energy probably fitting into the grid and then providing us electricity for driving cars. Or if we are using fuel cells, potentially providing for that hydrogen that we can use straight away close to the sourcing point. But if we need to then move it around, ship it, and send it long distance distribution, like in cases in the US where there are long distance pipelines, then it's probably the best way to then do it via ammonia. And if that's the case, we need to then consider how we're going to employ the transport, heating, cooling, process industry, propulsion, or stationary power. But still, there are many things that we don't know about and that we need to investigate. So some of them are related to reactions and combustion, how the addition of nitrogen is going to impact on emissions, how it is going to impact on the production of this energy via these sources. We are finding out, as I'll show you later, that there's some nitration combined with embrittlement when we start using ammonia for these purposes. Public perception is going to be a big one, because finally, people need to then understand how this is going to then affect them, how they cannot utilize some of these systems, and again, be aware of the potential risks that ammonia will bring. Regulations, there are none. Again, when it comes to fueling, and they've been talking about this for some time, but in the international arena, there's still nothing available. Economics needs to be profitable, and finally, the environment needs to be addressed as well, because we'll be dumping nitrogen somewhere that we didn't capture it, and same thing with water. So how is that going to affect the environment? And again, think that we're talking about gigawatts power being produced potentially using this vector. So that is something that needs to be addressed. So along those lines, and again, looking into why ammonia, one of the things that we always tend to mention is as well its energy density compared to hydrogen. So per liter and volume is obviously higher. And when it comes to what I mentioned, this long distance, long period storage, then it makes sense compared to the case of pure hydrogen. So shipping, rail, heavy duty lorries probably going to be fed using ammonia. But again, as I mentioned, it's not going to be the silver bullet that is going to solve everything. It's going to be just part, one addition of what is this hydrogen economy. So hydrogen is going to be there. So along those lines, some of the analysis that have been done looking into the use of hydrogen and other vectors, and this done by the University of Louvain, were trying to then demonstrate that by renewable energy production and then passing through all the different processes of electrolysis, storage, and efficiency of a final engine, the case of ammonia was very tempting. And you can tell from the comparison between methanol and methane that in ammonia is actually quite close in terms of that final efficiency. What is the main problem with hydrogen? Again, it goes back to the cryogenic storage. So if we're avoiding that part of the component analysis, obviously that final percentage comes much higher. And again, it just doesn't make sense to convert the hydrogen into ammonia. But if we need to then move it around and we need to store it rather than going cryogenic, we can go and then produce some ammonia. Finally, some analysis done by the University of Minnesota, where addressing how what would be the best scenario to employ either hydrogen or ammonia in different places across the US. So they compare 3 different scenarios, one hydrogen, the other one ammonia, and then finally combination of both. And then based on the location of the city, so say, for example, the case of Minnesota, Wyoming, that are in the Midlands and the central part of America, where you can then have more resources for farming, then ammonia makes more sense than having probably hydrogen pure. Whereas if you're next to the coast with offshore line a production system for hydrogen, then hydrogen could be the best option. So they address that, and depending on the location. And you can tell that based on that, some locations were more prone to be efficient or lower cost when it came to ammonia or hydrogen. But then when they combine both of them, it was the best scenario possible, because then what happens is that you reduce your capex, your capital cost involved in producing the ammonia, so you will require less ammonia at the same time that you will require less infrastructure for the production of hydrogen. Having a combination of both and then selling additional ammonia, then using that for storage, and then employing hydrogen directly in systems that can then use it instead of going to then reconvert it into ammonia and then back into hydrogen, made the best economic case. So beautiful and very interesting analysis done, which means that if we use that ammonia for, say, seasonal storage, or we have stranded energy, then potentially is the solution to then complement hydrogen. So the way that we see it is that both of them will complement each other, and then talking about that, then will then make the lower cost of the existing technologies that we got at the time. And on those lines, the International Energy Agency in 2018 finally addressed ammonia as an energy vector. Before then, if you go to 2017, 16, etc., you won't see anything related to ammonia apart from fertilizing. But then in 2018, it was finally addressed as one of the components of this energy mixture we'll have in the future. And on those lines, many different agencies across the world have been now taking this rationale and jumping on the train of ammonia as part of the energy mix. Everything is starting from Japanese that have now invested a very large program working on ammonia, and same here in Europe. In the US, we know Australia is one of the big players, and now we're hearing from developing economies like Chile, Morocco, India, etc., that are moving into this similar scenario. So along those lines, we have different ways to then use it. Once that we have produced the ammonia, we can employ it in fuel cells, can be used as well in internal combustion engines, as I mentioned, especially for heavy-duty processes, combined cycle gas turbines, and finally furnaces and boilers that have shown the best demonstration and the largest efficiencies of all the lot. But we have challenges. The challenges mainly are 4. First one, we need to produce it carbon-free, and needs to be a cost reduction in that cost and in efficient improvement. Because at the moment, the production of green ammonia is still very expensive. As we have it in the same way with green ammonia, green hydrogen. Green ammonia, because comes from that green hydrogen, is very expensive. And so one of the most expensive components of the total system is obviously electrolyzer, and then having the Haber-Bosch process is just a regular process that can be employed from fertilizing industries. But it's that cost of hydrogen that still just makes an important case when it comes to the cost of the final ammonia product. Power generation at utility scale needs to be stable and low emissions. We are still facing the production of NOx emissions that I'll mention later. They are not that bad. Actually, some of those are within the threshold. We're talking about high power outputs, but still we need to bring that down even further. Public perception and acceptance is a major barrier because people keep conceiving ammonia as a toxic chemical, that it is. But then the thing is that we've been working and using it for over 150 years, and many refrigeration systems are now running on the use of ammonia. So we know how to handle it. Problem is that it's not for everything. It's not going to be fed into pump stations where everyone can have access to it. It will require training, will require acceptance, and then community engagement to actually make it happen. The economics, as I mentioned, need to be profitable. Otherwise, there's no way around these technologies. So some of the work that we have done has to do mainly on thermal systems, as I mentioned before. And the work that we do has to do with studies of combustion and flame propagation. So you can see how the change and velocity of these flame fronts has changed based on the amount of ammonia that we got. So we have 100% ammonia. You saw how that bubble at the very beginning was just very slow, whereas the other two, for example, in the case of methane, was a little bit faster. And then finally, the one that was combined with hydrogen was much faster. Now, one of the questions that I always get is like, how are we getting that hydrogen? How are we going to then input hydrogen from that ammonia? Well, cracking the ammonia. So if we crack the ammonia, we can then recover some of that hydrogen and then use it to then boost the properties of pure ammonia. So instead of having something that is very dull and slow, we can have something that is close to what is natural gas. Along those lines, there's been loads of research looking into how we can then analyze and understand the reaction mechanism using ammonia and ammonia blends, and the work that is out there is massive. Just to give you an idea, some of the things that we have been doing, look into the analysis of 86 different reaction mechanisms that contemplate, to some extent, ammonia combustion. But the problem is that we still find that many of them don't provide reliable results. So they work nicely under the conditions that they were generated or designed for, but then when it goes outside of those conditions, then everything starts going bad. So this is one of those examples where we analyze 64 different reaction mechanisms, and you can see how those that are the very top have the lowest error between the numerical analysis and the experimental result. And you can tell that just changing the amount of air to fuel that we call equivalence ratio is going to then have a massive impact on the reliance and validation of these models. So some of them will be really good. Some others will just go and then provide zero correlation to what experiments are providing. So again, it's just a very interesting, nice area of research where we have loads of different researchers working on as we speak. Similarly, one of the things, as I showed in the propagation of these flames, is how would be the impact of hydrogen as we add it into ammonia. So one of the things that people have been experimenting on is this propagation of the different flame fronts. And as we start adding hydrogen, then what will start happening is something called hydrodynamic instabilities. And you can see how the change in the bubbles that we had at the very top with very low amounts of hydrogen are very nice, consistent, and propagate in a uniform form. But then as we start increasing the hydrogen content, then what will happen is that we'll produce wrinkles along the flame. And those wrinkles are going to then propagate and produce loads of instabilities that can potentially lead to the hydrogen, and they eventually will lead to the hydrogen taking over the flame. And if that's the case, it's very difficult to control. We'll have lots of different issues that will impact on what we call instabilities. So the instabilities will be the propagation of the flame inside of the combustion passages. So as we start adding more hydrogen, then what will happen is that we'll just flashback, and then that potentially can lead to disaster. Now, another thing that is really interesting is that once that we start adding more or less ammonia, then the flame will change because of the radical formations that we'll got. And this is something that is very tangible, as many people have been looking into this propagation of different flame fronts as, again, the change of the radical formation. So in my left, you have all these analyses using different amount of ammonia. And when we have zero ammonia, we have a nice bluish flame as the ones that we have in our ovens or equipment that we use with natural gas. But as we start increasing that ammonia content, then it will go more like in the orange spectrum because of the radicals that we're forming. And those radicals, we need them to then finish the combustion and then provide for enough reactions to finish the and annihilate the NOx that we're producing. So that's something that has been studied. And for example, we have a very good collaboration with the University of Orleans here in France. And what they've been doing is looking into how the mixture of ammonia and hydrogen and methane can change that reactivity. And here in these graphs, there's a massive change of that reactivity based on the amount of hydrogen or methane that we put into the ammonia blend. But one of the things that was really interesting coming out of that study is how much hydrogen or methane we're allowed to put in before we start seeing massive changes into what is the stability and the flame reactivity of these blends. And they found out that when we pass the 20%, then we start suffering big changes between one and other composition. So if we, for example, go with 20% hydrogen or 20% methane, then we can still use the same type of system. So same burner, the same nozzle, the same gas turbine potentially could be used if we replace just 20% of hydrogen with 20% of natural gas and the other way around. But if we pass that point, then that's when things start going different, and then we can have potentially these instabilities occurring in our system. In the same way, once that we start mixing up some of these blends, then what will happen is that they will produce these hydrodynamic instabilities. And that's the case, for example, as you see in some of the numerical simulations that some of our partners from Eindhoven have been doing, that very high ammonia content, the instabilities are reduced, are there, but not very acute, as if we have just 25% ammonia compared to the rest of hydrogen, so 75% hydrogen. The instabilities are massive. So again, going back to the part of combustion, the use of hydrogen is very challenging just because of these instabilities that we know happen when we start burning it. Another thing that is interesting to look at is people talking about the way that we can then use ammonia is direct injection. Because as I mentioned before, once that we got it at minus 30 degrees Celsius, then it will be liquid. Or if we just slightly pressurize it at 10 bars atmosphere, then the same phenomenon will occur. And why not inject it directly as liquid? So that's one of the areas that now several universities, including us, are looking at. So how we're going to then inject it in a way that will be efficient and will allow us to then provide for power systems that are reliable. And this goes in line with internal combustion engines, but also can go up to systems that are based on aero design, so aero gas turbines. So if that's the case, we have some scenarios where we are close to then that flashing point, then things will start getting very chaotic. But if we are far away at higher pressures, then that can be controlled. So that's a subject that we are now evaluating, and some other universities are also analyzing. In the same way, what if we use some of that oxygen that we recover from the electrolysis process and then put it into the combustion of this ammonia with some other species? So some works have been going, especially when it comes to natural gas and coal, because as I'll mention later, coal is a very important factor now, especially in Asia, that is being replaced using ammonia. And the results are very encouraging, because what the results are showing is as we are burning ammonia and coal, then what happens is if we oxidize it even further, then the amount of heat flux and radiation that comes from those blends is even higher, increasing the efficiency of power plants. So looking into the areas of injection, there's a lot of work going on, but still there are problems regarding the emissions because we don't have the efficiency as we got it when we vaporize it. So again, an area that is very interesting, this one on NOx emissions. And along those lines, there's been a lot of work on plasmas. So now we know that if we start employing plasmas to produce those radicals upfront the flame, then what will happen is that we essentially get everything ready to start reacting before reaching the flame front. And what that produces is a reduction in NOx emissions and also an increase in stability. So that's a fascinating area that just started a couple of years ago and has been led by Georgia Tech and other universities in Saudi Arabia. Some other developments that we got, again, passing the fundamentals, are more in the areas of practical applications, internal combustion engines. So we got an engine in Oxfordshire that is developed to burn hydrogen ammonia, the hydrogen at 30%, ammonia 70%, that is quite stable. The work has led us to then consider some scenarios that look into this potential of using ammonia as a method to then store hydrogen and distribute it long distances. So the way that we're evaluating it is we have some offshore winds, turbines running in the North Sea, and then that is a location where we produce the hydrogen. The hydrogen is distributed to a Haber-Bosch location, and then from there is moved around to this side or Milford Haven here in Wales. And once that happens, we distribute it and then finally reach some city gate terminals where we can then decide either to convert into hydrogen that will go into the cities, because again, we know public perception in cities is against ammonia just because of the smell, whereas in the case of rural locations, they are very much for it because they are aware and are used to manure smells. So they say, as long as the threshold of exposure is not going to be an issue, we are okay with that. And that's something that, again, in the US is probably ahead of the way that we got it here in Europe. Again, in terms of legislation and environmental policies, depending on the sites, but it's something that, again, we need to learn about here in Europe, especially if we're going to then think about having heat, cooling, stationary power, heavy-duty transport using this chemical in these rural places. And along those lines, there's been a lot of work going on in internal combustion engines since the 1933 to now these days, where we hear research institutes, companies now jumping on the train of using ammonia as a hydrogen provider. And the latest is the use of ammonia for trucks that are just moving heavy load in Canada. In the same way, marine applications are probably the ones that are just making the big noise, because it's been talked now, most of the forecasters believe that a third of all the fuel by 2040 is going to be ammonia-based for all these applications. We already move ammonia using shipping, so why not use it for fueling applications as well? So there's expertise already, and now the idea is to then develop the engines that are just efficient enough to then provide for a stable operation while also reducing the emissions and impact risk to the personnel and staff that is on board. And then finally, as I mentioned, farming and heavy-duty applications. Now, there's a lot of work, especially in the US, by the University of Minnesota, that is leading some of this work in combination with diesel and ammonia injection. So there are a lot of different aspects that have to do with internal combustion engines, from spark ignition to compressed ignited. And then depending on the different situation and the blend that we're using, either it's hydrogen or ammonia with syngas or with gasoline, DME or diesel, then the emissions and the performance will change. So again, it's a very interesting area of research that is showing that depending on that amount of air that we got and fuel, and also the pressure that we have for the engines, will change our final efficiency. So these are just examples of some of the work that has been conducted at the University of Orleans. We have as well a program with the University of Nottingham where we are looking into developing our own marine engine, and the numbers are very much alike to this one. So you are increasing the NOx emissions as you're adding more hydrogen, but then what happens is that that final ammonia on board is just going down because you're improving the reaction. So how to then manage both of them? There are a lot of thoughts and a lot of ideas, like a spark-assisted compressed ignition, the homogeneous control ignition, and also stratified control ignition. These are some of the works and some of the results that have been produced by the University of Nottingham, showing how if we increase that pressure and the RPM of those units, then we'll improve the efficiency and reliance of these internal combustion engines. So our final objective is to have one that will be able to be set up in a marine environment and run for a long period of time. Some of the work that has been done as well, some of the colleagues that we got in China are looking into how inject different amounts of ammonia via normal gaseous or injection, then using spark plugs assisted or even jets. And depending on the nozzle configuration, the geometry that they're using for the system, then that combustion efficiency will increase, the combustion duration will decrease, and the impact of these blends on the final material will change. So again, it's an amazing area of research. We're still learning about it. Each of these simple scenarios, each of them requires its own time, its own dedication, because again, there's lots of things that can be learned from any of them. So here are some of the results showing the difference between having RCCI and SI, the reactive control, and it shows from the University of Orleans that as they are increasing the amount of ammonia, the pre-mixing that they're doing, and also the duration and the delay of the spark, then that will have an impact on the final efficiency, the final amount of diesel, and the N2O that we will produce. So again, a fascinating area that has lots to give for the near future. Development in boilers and furnaces is another area that we are looking at, and it's a very promising one. It's probably the one that is going to be for our thermal system, the one that is going to be commercially available in the near future. And I show you here a photograph from a Chinese group in Foshan, where they demonstrated the first ceramic kiln worldwide using ammonia, pure ammonia. And they have a system that is producing these units, and apparently they have between 30 to 40 companies just in the region ready to then start switching from natural gas to this fuel. Along those lines, we are doing something similar here in UK. So we have a project that is looking into the replacement of propane, because propane can be as well stored at minus 30 degrees Celsius, so very close to the way that we do it with ammonia. And the way that we evaporate it, the way that we move it and handle it is very similar. So that's one of the reasons, because many companies working on propane, they're thinking that ammonia could be the potential solution to replace fossil fuels. And results from economic studies and initial analysis doing combustion, they show that we can do that very efficiently. So right now we're in the process of running a 2 megawatt power boiler that we're going to then, we have started replacing and we have started developing with the aim that having in a year and a half from now already functional in a poultry here in the UK. And some of the work that we have done as well is using humidification. So we tend to then add some water into this, and then that reduces even further the emissions. Now, one of the points that we always get is like, yes, that is going to reduce the emissions because you're reducing the temperature. Point that in combustion has to do with thermal NOx emissions, but that's not the case. In our case, we're running, yes, at a slightly lower temperature, but most of our emissions come from the fuel. And when that happens, and this reduction of emissions actually comes by the production of hydrogen and oxygen radicals that are now adding to the mix of all these radicals that we got in this vicinity close to the flame that are going to then start bringing down those emissions. So it's got to do more with the chemistry than with the temperature. In the same way, as I mentioned, one of the things that the companies in Japan are doing, and now in China, is replacing ammonia, replacing coal by ammonia. And I'm talking about power plants that are 1.5 gigawatts in power. So the latest was 3-4 months ago. Japan, a company run by JERA, has announced that they replace 50% of their coal in their power plant, in around 1.5 gigawatts power replacement purely on ammonia. And the reason for that is that, as I showed before, we have all these radiation, improvement in emissions, and the same onboard ammonia that they got coming from the stack is reacting with the NOxes that are being produced by the combustion of coal. So in that way, both of them are annihilating each other and therefore bringing down the emissions at the same time. How is that going to affect the systems, the materials? We still don't know. We're learning about it. But the idea is that by the end of this decade, they're planning to have 100% ammonia running facility that was running on coal just 2 years ago. Then we have some other areas, very interesting gas turbines. That's our main trade. And it was something that was really interesting because at the time that we were presenting some of this data, the Japanese groups were also presented it in the same symposium. So it was really nice to see that independently we showed similar trends. And essentially what we're saying is that if we run with a depletion of air in these combustion systems, then what will happen is we'll start producing lots of hydrogen. And that hydrogen is going to be potentially burned in secondary zones. So we finish the combustion in what is called multi-stage combustors, because the second stage is essentially a hydrogen stage of combustion. So if that happens, then the emissions are extremely low, the power that is coming out of that is extremely high, and we have a reconversion and efficiency of these systems higher than 99%. Along those lines, we have done lots of different analyses based on the flame and how it reaches different locations. And as I mentioned, when it comes to the flame front, it usually tends to be the same, depending on what are the conditions that we are using. Again, it can be retracted, the flame a little bit thinner, etc. But it's this post-combustion recirculation and post-combustion reaction that we want to enhance to then bring down the NOxes. And that is doable without having to use selective catalytic reduction. Along those lines, we're looking into the position of those flames and how the radical formation is going to impact this reduction of emissions via the recombination of radicals. The ones that are more important for us are OH, CH, NH, and NH2. And depending on where they're located, we're targeting those areas to then bring down the emissions. So that's something that we're doing at the moment. We are using stratification and developing our own burner. So this that you can see, this photograph, is a patent that we just got granted 3 months ago, and it shows how using stratification, location of these radicals, and a proper control of the temperatures, we can then manage to bring down the NOxes that you will get from these combustion systems. And that is being supported by all CFD modeling that we've been doing with partner institutions. We work a lot with universities from India, from Europe, from Japan, and also we're starting now to work with the US as well in this front. Another topic that is really interesting when it comes to these thermal systems is material science. And one of the main problems is that people haven't addressed this point yet. So it hasn't been a problem for any manufacturer. So we started working on this and looking into how hydrogen and ammonia could then impact the different materials we were using, especially for gas turbines. And you can see from this photograph that A has been exposed to ammonia hydrogen, B to methane. There's a massive change in what is the reaction happening at the surface level and just below the surface level. And it's a combination between nitration and also hydrogen embrittlement. So if we have gas turbines as they're designed now with the materials that they've been using, employing ammonia or hydrogen, then what will happen is that a combination of both nitration with embrittlement will then annihilate or destroy the components. I'm talking about gas turbine components like combustors or blades coming in the turbine. So it's an area that requires a lot of research. Another part of the research that we're doing is looking into high pressurized systems. So we are evaluating, as in a gas turbine, high pressures. And one of the things that we're observing is that as we increase the pressure, then NOx emissions come down. But then another thing as well that is really interesting is that as we increase the swirl or the recirculation of these species, that as well is going to impact the NOx abatement. So again, lots of areas to do analysis on. These are some of the players that are developing right now micro gas turbines, and mainly based either in Japan. Some are now showing up in China. There's been a lot of work here in Europe, and there's now some talks that in the US, both a combination of Central Florida and Georgia Tech in a joint program will develop their own. But this is an area that requires a lot of research and development, as it can be one of those points of application where we can then develop these units for farming or stationary power. Some other areas that are also of interest are propulsion. So as I mentioned before, ammonia has been considered as well as a propulsion fuel. And this goes back to the work that the US and NASA were doing a few decades ago. So the X-15 Viking program was actually developed using liquid oxygen and ammonia, and the velocities that they reached almost to 7 Mach were closer and were never beaten until the shuttle was released a few years later. Russia, China, and some other economies are using ammonia already in satellites, but the idea is that eventually we can then use it again as a replacement of kerosene. So here is a comparison between what would be a liner running on the same amount of volume with either jet fuel, liquid biomass, liquid ammonia, or liquid hydrogen. And the comparison is, again, for zero carbon fuels, that ammonia will be superior to the case of hydrogen. It's just based on what I mentioned before, that the amount of hydrogen that we're carrying on using liquid ammonia is much higher than the one that we'll get using either liquid or compressed hydrogen. So that opens lots of different aspects to then use that chemical. Some thermodynamic analysis have shown that it's doable. It's going to be closer to what we got with kerosene, but at the same time, it shows that a combination between ammonia and hydrogen could be the most feasible solution. The table shows from 5 being very good or excellent to 1 being very problematic what are the issues when it comes to the use of these blends. And as you can see from the combination of ammonia and hydrogen, the very last one, is that toxicity becomes the major issue. So in thinking about ways on how to then handle it, store it in case of a catastrophic situation, what would be the case to then reduce and minimize all that exposure of the ammonia being released? Because if it's released and we then suffer, then can end up with this situation. So this is the exposure of the skin to ammonia, and again just kills the cells. It just drags all the water and then finally kills the skin. So it's one of those points that when we talk about toxicity, and this is something that has been covered by the Ammonia Energy Association, is that it's actually not toxic for humans, but actually corrosive. Because if we get exposed to one of these clouds, what is going to happen is that our throat probably will burn before we actually can inhale enough ammonia to die. So it's going to be the burn of our throat that is going to kill us. Again, the lack of breathing. In the same scenario, it can produce explosions. And if it's pressurized, then sudden release can create a mist, a deadly mist that again can lead to these scenarios. But at the same time, one of the things that is very interesting is that although we have these potential fatal scenarios, the case of ammonia is quite good compared to some other chemicals. It's the second most worldwide commercialized chemical, and still the report of fatalities in the developed world is quite low. Here is just a few numbers showing the fatalities that have been recorded over the last 50 years. And as you can tell, it's less than 50. And we're talking about, again, fertilizers and refrigerators that are running everywhere in every state in the US. So the track is quite good. Similarly, some studies done a few years ago, they note how if we compare it with LPG, it's actually much better because we eventually will start smelling it. And again, its dissipation won't be immediate. So if we have a leak of ammonia, it's not that it's going to then convert immediately into vapor. It's going to take its own time, its own energy. And then based on that, there's enough time to then raise awareness. So that again was part of the study. And another study that was recently released just a few months ago was a comparison. What if we had them fueling ships and vessels? And they compare the Environmental Defense Fund, what would happen in that scenario where we'll have oil spills versus ammonia spills. And looking at this, the main problem for ammonia will be fish, because for fish, it is toxic. It just becomes diluted, and then as the fish start ingesting it, it will just get to a point of killing them. But that compared to the oil, that will kill invertebrates and birds, then it's showing similar potential impacts. So again, it's not as bad as it could be. It's just that training and then the use on its special and niche applications. Some other study done recently by some of our members in the US, what they evaluated was, what if we use some selective catalytic reduction in transport? And they define these different scenarios. So we have those that don't have any treatment, post-treatment, as we finish the combustion, and those that have it. And those that have it are within the threshold of the same emissions that we're right now producing using diesel, which is again quite good. But that depends as well on what state we're talking about. So if we're talking about, for example, New York or California, where there's lots of cars and already a very strict regulation regarding emissions, then becomes a problem. But if we're talking again about Minnesota, Iowa, places where we have lots of space and there's no much problem regarding these environmental impacts, then it becomes the potential solution. So there will be, again, loads of different scenarios where we can use it efficiently. Some other studies that we have done, public perception relate to the use of ammonia. And we evaluated two different scenarios, one being a developing economy, Mexico, and the other one developed economy, the UK. And it was really interesting to see that after doing almost 800 and 900 in different interviews, 920, then from the UK, we saw that the main problem was the smell. Whereas in Mexico, the main issue was actually the poisonous toxicity that ammonia could cause. And this goes back to regulations, because we know that in Mexico, the regulations are quite loose, whereas in the UK are very strict. So again, it goes back to that public perception problem. So where are we going? We're going into potentially having large power stations, as I mentioned, gigawatts power. We are talking now 2025, 2026, Mitsubishi having the first pure ammonia gas turbine being powering up to 40 megawatts power. NASA with Georgia Tech and Florida developing a Boeing, fly that will be burning ammonia, will be using ammonia as a method of transporting the hydrogen, and then providing for the cracking using a waste energy. And then finally, some ideas that are just coming on board that ammonia will eventually be produced offshore. And then it won't touch the coast, it will just go to its final destination. So along those lines, these are some of the collaborations that we got working on this program at different levels, from very fundamental to large-scale demonstrators, and some of the programs and conferences that we're holding now. Anyone interested in any of these, please go and join our websites, or just give me a call or send me an email so I can give you more details. So as a conclusion, ammonia can be used to decarbonize cooling, heat, power, and propulsion. We need to do it efficiently with low emissions, and also we need to then understand how we're going to then manage all these combined processes, because it can be done as demonstrated by coal combustion. There are still many points that we need to address, especially when it comes to combustion and thermal system. So it's a fascinating area to explore, and we believe that is going to be part of this hydrogen economy, something like hydrogen through ammonia, that will support us into getting into that final decarbonization for the world. Thank you very much. And is there any question?
Thanks a lot, Agustin. Really interesting. We have a question from Charles, actually. So it is provided in Q&A section. The question is about your HSE numbers. So do your HSE numbers take into account the smaller amount of ammonia transported? If there are fewer ships, trains, trucks, then there will be fewer accidents. Increased presence could lead to more accidents. Fair question.
Yeah, no, that's a very good question. Actually, the model analyzes and uses the current mobility of ammonia. So as I mentioned, it's the second most commercialized chemical. And you're right. I mean, one of the things, I mean, we start thinking about a fueling as a fuel, then it's probably that we'll have to think in ways that we can handle the amount of ammonia that we're moving around. One of the main problems that happens, for example, in China, is that they suffer a lot with the tankers. They again don't follow regulations, and then suddenly have car accidents, and that obviously spreads all the ammonia and then ends up killing between 10-20 people in one incident. Whereas in the US it is not the case, because again speed regulations are more strict and followed than in China. But if this becomes something that is widely developed and provides for a fuel for the future, then we'll need to find some other ways to do it, as the ones that we have been doing it. So yes, the size will matter. Also, for example, in the shipping applications, people developing these new ideas, architectural firms, they are looking into how big these tankers for the fueling need to be, not only because of how much fuel we can move around, but also again on that aspect of if we have a leak, how we'll be able to then cope with it, because having it released is not an option. Again, anyone on the ship can potentially die. The second one could be, can we mix it with water? Well, we can sink the ship. And then the third one, we cannot release it to the environment, will kill all fish around. So yes, again, is one of the big questions to answer in terms of health and safety.
Good. Thanks, Agustin. There is another question. What about soot formation from unburned ammonia emissions? Has that been looked at?
Yes, that's as well a very interesting question, because when it comes to all these sleep ammonia, one of the main problems is that it starts getting mixed with some sulfates and nitrates in the atmosphere, and then producing soot, which is one of the main issues when it comes, for example, to fertilizing applications. That's one of the big problems when environmentalists are looking at. So whatever technology we can come up with, it needs to then have as low as possible sleep from the exhaust. Otherwise, we'll be just dumping ammonia. And again, ammonia per se is not a problem when it comes to greenhouse effects. It just dissociates almost immediately, but then dissociates into the soot that can then potentially be very damaging to humans and life forms. So yes, any solution that we come up with, it needs to then rely on, we are not producing NOx emissions, or again, a very low NOx emissions, and sleep ammonia as well is reduced to its maximum. Otherwise, we'll end up with soot formation anywhere we're using it.
Good. Thanks a lot, Agustin. The final question from my side. Similar to hydrogen, ammonia also has a range of different applications. And I guess ammonia could be more competitive in some applications and less competitive in other applications. In terms of hydrogen, recently there is a so-called hydrogen ladder concept coming out, showing the applications and sectors in which hydrogen is very competitive and coming down to less competitive applications. Do we have similar things for ammonia? Ammonia ladder.
Yes, absolutely. We believe that the areas where we have a very good potential is long distribution. So, for example, shipping, when we're talking about, again, large containers that are just moving intercontinental goods. We believe that long distance traveling as well, for example, airplanes can then use it as well, because again, compared to hydrogen, is going to give us more hydrogen per se. So it can be cracked. It doesn't have to be directly fed into the system, but it can then provide for the hydrogen, and it's going to be more hydrogen than the one that you will get from liquid hydrogen. Heavy duty, so when it comes to internal combustion engines, we still believe, and many developers, including Cummins, including Rolls-Royce, including Ricardo, believe that internal combustion still will be around, especially for heavy duty, because fuel cells, they don't manage to then get that heavy load out. So it will be combustion based. And when it comes to heavy duty, again, more ammonia will provide for more power compared to the same amount of volume that you will get from hydrogen. Power stations in rural locations, long distance, again, and coal replacement of coal, replacement of natural gas. In large power, we believe as well, it will be a very good case to pursue, and chemical processes, because chemical processes as well require a lot of natural gas, and the amount of energy that is required is just so massive that we need a large density chemical like ammonia. It needs to be essentially big, long distance, and long storage. If it's something around those lines, ammonia has a play. Otherwise, no.
Thank you very much. While you were providing that answer, I realized that we have another question here, but because of time limitation, I hope this is okay, that you actually answer that question offline. So yeah. I'm sure that we can kind of provide those details, or if you can type it there, be excellent. Thank you very much, Agustin, for the presentation. Very informative and lots of interesting questions as well. For next month, we are planning to organize a kind of some sort of open discussions. So there is not going to be any presentation or talk. This is going to be a virtual table discussion around hydrogen and role of hydrogen. We will plan that session and provide you with more information soon. Thank you very much, everyone, and I hope you enjoy the rest of your day. Thank you. Bye.